Hello, class. So I decided to upload one more video on section 5.3 because I wasn't sure if we did this type of example in my math lab, but it turns out that I got a question from a student and we do work over an example like this in my math lab. So let me just give you just one example. It should be enough because they're all basically the same process. But the idea is that suppose you're given to simplify or evaluate an expression like this, and some function here, let's say 1 over, uh, let's do p to the fourth plus p, and then dp. So I'm going to write it like this. Suppose that's the problem you're given. Oops. Like that. So you want to take the derivative with respect to x of this expression here, the integral from negative x to x of dp over p to the fourth plus p. So let me make a few comments before we start. So this is a question about the fundamental theorem of calculus part 1. Right? So taking the derivative of an integral, that's the only case where we've seen something like this. But first, let me make a note here that whenever you see something like this, so dp over p to the fourth plus p, so I mentioned this in passing in one of my videos, but here let me make a little bit more emphasis. This is the same as 1 over p to the fourth plus p dp. So I mentioned in passing in my videos that sometimes they write the dp on top, just because it's simpler to write it like this than to write it like this, but it's the same thing. Right? So whenever you see something like that, don't get confused. So this is saying find the derivative of the integral from negative x to x of 1 over p to the fourth plus p dp. Right? So it's the same thing. Right? So don't get confused by that. Usually, whenever you have a fraction that you're integrating, they're always going to write the dp just as the numerator, part of the numerator of the fraction. But that's just notation wise. In meaning, this means exactly the same as this. So that's the first thing to note. Um, Now let's try to do this problem. So we want to use the fundamental theorem of calculus part 1. The only problem is that for the fundamental theorem of calculus part 1, we had an expression like this. Actually, it's just some constant on the bottom. It doesn't matter what the constant is. X, and then here's some expression involving whatever variable it is. In this case, since they're using p, let me use p here. And remember that the reasoning for using for not using x for the function that we're integrating is because we're using x as the input here. Because remember that this thing here, this is by definition the area function. Right? It's a definite integral. It's just the net area bounded by your function on the interval c to x. So you're looking at the interval here, c to x. So this is just the area function. So by the fundamental theorem of calculus part 1, as long as your function is continuous on this interval, right? So as long as f of p is continuous on the interval c to x, then it's easy to evaluate this because you just change the p's with x's. So all this thing here would simplify to just f of x. That would be if you had a constant on the bottom and just x on the top. In this case, of course, we don't have that. We have an x on the top, which is good, but we don't have a constant on the bottom. We have another x, in fact, negative x. So how do we deal with something like that? Well, we have to go back to properties of integrals. So first, let me notice something here. If x is 0, then this whole thing would be 0, right? Because we saw a property of integrals that said that the integral from a to a, this is always 0, always. And remember, the reasoning is you have a rectangle, the length of the rectangle is 0, and so it doesn't matter what the height is. When you find the area, it's always going to be 0. 0 times any finite number is 0. So in problems like this, you always want to assume, and make a star of this, you're always assuming that x is greater than 0. Or whatever bounds it is that you have here, it can't be just the same bound. So it can't be just something to itself, right? So in this case, x has to be greater than 0. If not, it would just be the integral from 0 to 0, right, which would just be 0. Now, the reason for doing this is because think of what this interval of integration is. We're doing the integral from negative x to x. How does that interval look like? Well, negative x is here, x is here. X is greater than 0. That's all we know. So in the middle is 0. Now, actually, let me go here a little bit more. So what's the reason of going over this assumption and noticing that we have this interval with 0 in between? The reason is that you can use this other property of integrals. Basically, what was that property? If you have the integral from a to b of f of x dx, well, this is the same as the integral from a to c plus the integral from c to b, with the only property that c is any number inside your interval. So this was that property that you can separate your integral into parts, as long as those parts add up to the whole. So we did an example like this when we were doing the geometric interpretation for finding definite integrals, where I had this picture and it looked like two triangles, so I could just find the area of each triangle separately. It's the same idea here. You can always separate your integral into smaller integrals as long as the sum of the intervals end up adding up to the whole interval. In this case, if we add up the interval a to c to the interval c to b, we get the whole interval a to b. Now, that's helpful for us because that means that we can rewrite the integral from, actually, without the derivative right now. Let's not worry about that. We can write this thing here. Since 0 is between negative x and x, this is the same as the integral from negative x to 0, 1 over p to the 4th plus p dp, plus, now we want to go from 0 to x so that the intervals add up to the original one. And in my math lab, they gave you this hint that you want to rewrite it like this. So this is just basically explaining where the hint comes from. So let's see what we've done so far. And actually, I only need this. I don't need to scroll up again. So this is what we're trying to find. And again, I mentioned if we had an expression that was a constant on the bottom, so go to look at the right-hand side here, a constant on the bottom, and x on the top, and we wanted to find the derivative of that, you would just replace whatever variable you have by x. So this would all simplify to just f of x. Again, the problem in our example is that the upper bound is x, but the lower bound is not a constant. So somehow we have to deal with that, and the way we deal with that is that we rewrite this integral, right, by separating it. Okay, so that's the first part. That's the first part you have to be comfortable with. So that's just explaining the hint. So let me go to another page. So what does this mean for us? Well, we rewrote the derivative of this expression. So we have the integral from negative x to x of 1 over p to the 4th plus p dp. We know now that we can rewrite this as the derivative of the splitted version, where we split this. So negative x to 0, 1 over p to the 4th plus p dp, plus the integral from 0 to x, 1 over p to the 4th plus p dp. Now, this is a derivative of a sum, so we can take the derivative of each term. This is d dx of the integral from negative x to 0, of 1 over p to the 4th plus p dp, plus d dx of the integral from 0 to x, of 1 over p to the 4th plus p dp. Just separating it as the derivative of each term. Now, if we look at both terms we have here, specifically at this one, now this is exactly what we had in the previous part, because what is this? So this part in red, so let me write it as star. This part star, this is exactly the derivative of a constant on the bottom, x on the top, of an expression involving p. Right? In this case, the expression being 1 over p to the fourth plus p. Right? So by the fundamental theorem of oh shoot. Okay, let me do something here. So if you remember, I mentioned that the condition for the fundamental theorem of calculus part 1 and 2 is that this function here has to be continuous on your interval. Here, p to the fourth plus p is not continuous on this interval, right? Because it's not continuous at 0. So in fact, just let me make a quick change. It won't change anything we've done so far. It's going to change the p with 1. So p to the fourth plus 1. Now that thing is going to be continuous. So just let me make that fix. So that's actually good that I made this mistake, because now we see a case where, the function is not continuous, so we can't use on the interval, so we can't use the fundamental theorem of calculus, part 1. And again, it's the same for the part 2. If your function is not continuous on your interval, then you can't do this, you can't use the fundamental theorem of calculus. Okay, so going back, let's erase, this should be 1, and then that fixes our problem. Now, p to the fourth plus 1, that's continuous everywhere. I want to repeat to the fourth plus 1, sorry, that's continuous everywhere. So now we can use the fundamental theorem of calculus, right? Meaning that, as we said before, as long as your upper part is x and the lower bound is a constant, you can just replace the p with the variable x. Meaning that this whole thing here, well, just replace the p with x, so this whole thing just becomes 1 over x to the fourth plus 1. So that's kind of like the easy part. Okay. Now let me make another note here. Using the notation that we've used before, remember that this part here, so whenever you have the integral from any constant to x of whatever function, again, let me just use p because that's the variable we're using right now. This is the same as the area function. Remember, what's the area function? Well, we're integrating on the interval c to x, and x is changing. So the area function, the input is the upper bound of the integral, which is the same as the right endpoint of the interval you're integrating over. So if you change x, you change whatever interval you're integrating with, because you're changing the right endpoint. Okay. Now, I mentioned this because this is going to be useful for this part here. And this is the same thing I mentioned in the videos at the end of section 5.3. I do examples, and you see that I always write this in terms of the area function. So I definitely go back and look, rewatch if you haven't watched those, watch the videos at the end, the examples at the end of the videos in section 5.3, right? So we took care of this part. Now we still have to take care of this part here. So somehow we have to take care of this derivative. Now, again, here we have a problem because our constant is on the top and our x is on the bottom. And it's not just x, it's negative x. Again, if we have something like a constant on the bottom, right? So actually, let me go to the first slide. If we have something like a constant on the bottom and x on the top, right? We know that to take the derivative of that, as long as your function f of p is continuous in that interval, you just replace the p's with x's, which is what we did here on the right-hand part. So what we want to do here then is rewrite this in a way such that the x is on the top and the constant is on the bottom. So how do we do that? You have to remember this other property, that you can always change the order of integration, so the bounds here, you can just have to add a negative in front. And we did examples of this in either section 5.1 or 5.2, meaning that we can rewrite this. We can rewrite this as the derivative, and then we'll just add a negative, right? So we can change this as, change the order of integration here, change the bounds. Then, of course, the negative is a constant, so we can move it out of the derivative. So we end up with this thing here, which now almost looks like something we can just take the derivative of, just plug in x, almost. problem is we don't have x on the top, we have negative x. And this is where we want to go back to the area function. So we want to write this in terms of the area function. Right? As we know, the area function would just be the integral from 0 to x of 1 over p to the fourth plus 1 dp. Right? So the area function is just the bottom is a constant, right? Whatever constant you're working with, in this case 0, and the top is x. That's the area function. The reason for writing this in terms of the area function is, if you look at this, this is almost the area function. Instead of x, you have negative x. And this is going back to those videos in section 5.3 at the end, where I said, whenever you have anything other than x here, what do? Well, that's the same as the area function composed of whatever you have there, whatever expression of x you have. In this case, it's negative x. And you want to write it like this, right? That's a composition of the area function with whatever expression of x you have there. Of course, if it's just x, you can take the derivative by just replacing the p's with x's. Here, it's not just x, it's an expression involving x, so we have that negative in front of the x. So just, again, what's the trick? Write it as the area function, and the input is whatever you have here. So for example, just to make this point clear, if you had d dx of the integral from 0 to, let's say, x to the fourth plus cosine x, that's an expression involving x. How could we rewrite this in terms of the area function? Well, this would be the derivative of the area function composed of whatever expression of x you have. In this case, x to the fourth plus cosine x. So it would be the area function. On the inside, you just write whatever expression of x you have. So it doesn't matter how complicated that expression of x is, you always just write the area function, and on the inside of the area function, you write whatever expression you have for x. And then why was this useful right now and in section 5.3? Well, because once you have that, you can use the chain rule, right? You can just use the chain rule for compositions. Meaning that what's the derivative of this? Well, take the derivative of the outside. So I keep the negative out front, right? Because I have a negative here. Take the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. So derivative of negative x. Now, of course, the derivative of negative x was just negative 1, so times negative 1. So that simplifies the negatives. Right? So negative times negative is positive. So it simplifies to this. And now we already know what this is. Why? Because we know what the derivative of the area function is. For the derivative of the area function, all you do is replace the piece with x's. Right? So remember, when we were doing compositions or chain rules, I always said you can do this in 2 steps. First, find a prime, and then find a prime of negative x. Just replace the x's with whatever expression you have in the composition. So what's a prime? Well, we know what a prime is. You just replace the piece with x's, right? So in the expression. So just replace the piece with x's. So what's a prime of negative x? Just replace x with negative x. Which of course you have 4 negatives, so that ends up just being the x's, the negatives cancel. So now we can go back to finish the problem, because where were we? Yeah, so we had found that this part here, the one underlined in red, was 1 over x to the fourth plus 1. And then here in this page, we found that the other part, so this part here, right, which is the same as this part underlined in orange, that we saw that also simplified to 1 over x to the fourth plus 1. So now you just add them together and you get 2 of them. Right. And then that's the idea. This is the hardest type of problem you're going to see, but the steps are always the same. So let's just review what we did. What do we do first? We realized that we didn't have a constant on the bottom here, so we can't just use the fundamental theorem of calculus directly. So we use this property where as long as you choose any constant inside your interval, you can separate your integral, right, into two parts. So that was the first part, right? Separate your integral into two parts. And again, that hint is given in my math lab. Then, well, we want to take the derivative of that new thing, so we can separate as a derivative of each term. Then it was the problem of finding each derivative, the derivative of the part underlined in red, the derivative of the part underlined in orange. For the part underlined in red, that's just the area function, right? Or you can, the other way you can think of it is just there's an x on the top, which is good. The bottom is a constant, in this case 0. That's good. What's the derivative of that? Just replace the p's with x's. Okay. For the other part, the part in orange, we saw that, oh, this is bad because the constant is on the top and the x is on the bottom, right? So we use this property where you can change the bounds, you can change the order, you just have to add a negative in front. And that's what we did. Then we saw, okay, we're still not done. We still can't just replace the p's with x's because this is not an x, it's a negative x. And again, at that point, I said, you want to think of this in terms of the area function. Right? So whenever you have an expression that's not just x, but an expression of x, that's just the same as the area function composed of whatever expression you have. So I did that, I wrote it down like this, and we also did an example here. Then after that, then it was just using the chain rule and then simplifying the chain rule. And then putting everything all together in the end. Okay. So this should help you finish the problems in section 5.3. And this basically encompasses everything you're going to do with the fundamental theorem of calculus part 1. And it also reminds you some of those properties of definite integrals that I mentioned. They're not going to be as useful for us right now, but here you saw they became useful, right? So changing the order of integration was useful. Rewriting the integral as integral over separate intervals, right? In this case, the interval from negative x to 0 and then from 0 to x. So this should help you. If you have any questions, again, just let me know.